All right. I was requested to do this, and I was happy to do it because currently any discussion I have on Newton and bisection method are embedded in the middle of another seminar, so I thought that I could do it straight up. So the subtitle of this is sort of finding approximations to zeros of functions. I mean, that's what it is. That's what they're for. They're both for this purpose. So each of them has its advantages and disadvantages. So the bisection method, which I will put down in a minute, the bisection method has an advantage that it always works. Always. It has a disadvantage that it takes a while. It might take a very long time to get the accuracy you want. Newton's method has an advantage that it's very fast. You only have to do it a couple of times to get to a really quite high level of accuracy. And it has a disadvantage that sometimes it doesn't work. And when it doesn't work, that usually means you have to go back to the beginning and start again. And so it ends up taking longer than you hoped. Whereas bisection method never has that problem. You just gun it, and it might take you ages, but it'll always happen, and you'll never have to backtrack and go back to where you were. So these are the two methods you've currently got of finding zeros of functions, and your graphics calculator, which you're not allowed to use in your exam, but for interest's sake, your graphics calculator in general will use the bisection method, but some graphics calculators actually use Newton's method if they've got CAS built into them. So it's pretty cool. Okay, so I shouldn't have done that. So Newton's method and bisection method. I'm going to do bisection method first because it's the easier one, and then I'll do Newton's method. So let's see. The bisection method is based on the intermediate value theorem, which says that if a function is below the x-axis somewhere and above the x-axis somewhere further on, then it must be on the x-axis somewhere in between. So that's basically it. You just keep cutting it in half and seeing which half it's in based on whether it crosses the axis in that zone. So best to do with an example. I'm just going to check something. Okay, it's not at all obvious for different people who write these notes or the assignment questions or people who you're talking to, it's not at all obvious what they mean by approximation x1 or x2 or x0. So you'll just have to be clear when you write it yourself so that the person reading it can understand what you mean. So here's an example. I don't know. Well, you can help me figure out a zone where I want to find a zero of this function. Tell me a place where this function's negative. I'm not going to, you know, 0 is obviously a zero of this function. I told you that to sub in 0, you'll get 0, so not that one. So tell me a number other than 0 where this function is negative. 2? Yeah, that'll work, because sign's always... sign's always negative, sign's always less than 1, and so sin x minus 2 will have to be negative. What about a place where it's positive? Yeah, minus 2. But we don't want to include 0. But minus 2 is a very clever answer. I liked it. Somewhere, let's say not 0, something more than 0. Is it positive at pi? No, I don't think it is, because it's like 0 minus pi, which is negative pi. Oh, I suppose it's sorry, what was that? Pi on 2. That'll work. No, isn't that still negative? Pi on 4? Let's find one. Damn, who's got a calculator? I know, I've got a phone, that does it. Can't use that in my exam, though. Not that I'm doing an exam. Sine of pi on 2 is 1, right? Yes! All right. So I'm going to say 1.5. There we go. Thank you. 1.5 and 2. Right, so the way this works is that we are going to figure out what my function value is at those points. I don't really care what the function value actually is. I just care that it's positive or negative.
Were we looking for a positive value at 1.5?
Is it not positive at 1.5?
Is it not about negative?
Oh, frelly. It's one of...
One take 1.5.
Which is still negative. All right. Don't tell me there isn't another 0. That would be really depressing.
I don't think there is.
Yeah. Great. So 2 will still work. It'll still be negative there. And 1.5 will now work. Will it? Brilliant. Aren't we lucky that exam questions don't go, write an exam question for this concept? Okay. Right. So let's just check that. F of 1.5 is what? What does it actually come out to? And f of 2 is what? Okay. So it crosses from being positive to negative on that zone. So it's positive over this side, and it's negative over this side. So we know that the function has to cross the x-axis between them. That was the whole thing about trying to make sure one was positive and one was negative. So I'm going to pick the point halfway between. So my x1, I'm going to call it, is halfway between 1.5 and 2, which is 1.75. If you want a method for calculating that, you'll average those two. So 1.5 plus 2, then divided by 2. But I can do that one in my head. Okay, so I'll do f of 1.75, and what does that come out to? Have we got an answer?
0.1089.
Okay. So, at 1.75, it's positive. So which side is the 0 in? The left-hand side or the right-hand side? Yeah. The right-hand side, which is where I am. From your perspective. So that means I've got a new interval, which is like this. Like that. And I need to divide this one in two. So x2 will be the average of these two. Which will be 1 point something. Cool bananas. And so f of 1.875 is what?
0.0165.
Which is still positive. And so the 0 is in this zone, because that's where it crosses over. What's this one?
937.
And what do we get? What do we get when we do f of that?
Negative 0.0352.
So it's negative here. I'm drawing the negatives below and the positives above, and so it's now in this zone. That's as far as I'm going to go, just because I can't be bothered doing any more of those. And so my final estimate's going to be this one in the middle, since I might as well average them. So that'll be this plus this divided by 2, so 8.
1.906.
Now, if what I wanted was to do this to 3 decimal places, I'd have to keep going until I was sure that my first 3 decimal places didn't change. So I have at least got it to 1 decimal place now. It's definitely 1.9 to 1 decimal place. Because I knew that either of these will round off to 1.9. So when I round off to 1 decimal place, it's going to be 1.9 either way. So approximate 0 is 1.9 to 1 decimal place. There are ways of doing the bisection method a little more cleverly, because if I only wanted it to 1 decimal place, why would I care that this went to 5 decimal places? That's completely irrelevant. And so you can actually round off as you go to whatever accuracy you're aiming for. Well, 1 more decimal place from the level of accuracy you're aiming for. So there's no particular reason why I had to use 0.875 if I was going to go for 1 decimal place. I would have used 0.88. So it's okay. So I'll just make a note. Okay to round off the xi's as you go to match the level of accuracy you want. Okay, so if all I wanted was one decimal place, then I would have rounded this off to 1.88. I just done it with one extra decimal place just to make sure that I'm not losing anything good from that. Right, there we go. Because if you round off to one decimal place, you'll always end up getting the same answer, so you want to make sure that you do it a bit more precisely than that. That's the bisection method. Newton's method is even, I mean, that's just fancy at all. I have to say I was proud of myself one day when I figured out this diagram. It helped me so much. Yeah. So each one of them is like a zoomed in version of the one before. So if I was being particularly nice, yeah, gets bigger as you go down. Anyway, that's just me. What I really want is an animation where it actually zooms in. That'd be cool. Okay. Now Newton was a very clever man. He invented the cat flap, which is a supremely clever idea. And he also invented Newton's method, which is less clever than the cat flap, but still pretty good. So, Newton's method is based on this concept that the tangent to a curve, if you zoom in really far, the tangent to a curve looks like the curve does when you zoom in really far. So if you happen to be close, roughly close to the zero, then it should be okay to do something about the derivative to get you to where the zero is. So that's the philosophy. So the philosophy goes that if I have a curve that looks like whatever it looks like, and I pick a tangent somewhere, like that, if I zoom in here with my magnifying glass, here I am trying to zoom in with pencil and paper again, then the tangent and the curve are not all that different. And so the philosophy goes that instead of figuring out where the function meets the x-axis, I'll figure out where the tangent meets the x-axis, and that will be my new estimate. Yay. So there was a famous past exam as well. Could have even been the same one. There was this one exam a couple of years ago that was really hard. Who's your calculus lecturer? Oh, I have no clue what Luke will do. Sorry. If it was certain other lecturers who have what I call lecturer boredom and write exam questions based on how cool they think they are rather than how easy it is to do them, you have a problem. Luke, I think, seems to be okay. Ray is awesome. I love Ray. But he's not teaching you calculus. So, those of you in a future semester who've never heard of these people because they don't exist here anymore, sorry. Okay, here's the proof of how it works. It goes like this. Here's the x-axis. I don't really care where the y-axis is at this time. And here's my function. Maybe not like that. Okay, so here's my function, y equals f of x. Here's my tangent. And here's my current estimate, xn. And my next estimate is going to be this point just here. Just so that we can see everything better. That's my function. And that's my tangent. Okay. So I want to know what this point is here. That's what I need to figure out. This point here is xn f of xn. That's how I figure out the y-coordinate of that point. I sub xn into the function and it tells me what the y-coordinate is. Now, here we go. This point has a y-coordinate of 0. Like that. So one more thing to notice on this diagram. I know what the slope of that tangent is. It's a derivative. That's what derivatives are for. Well, it's one of the things that derivatives are for, figuring out slopes. This is all the information I need to prove, not prove, but derive Newton's method. It goes like this. Let's see if I can fit this all on the screen at the same time. The slope of that red line is f dashed xn. But it's also the slope between these 2 points, which is the change in y divided by the change in x. And when I rearrange this, I get Newton's method. I can put this up there and that down there. And then I can add this to the others, to both of these parts. Whoops, sorry. And that's Newton's method. That's how to derive Newton's method if anyone ever asks you. It has been asked in past exams, just so you know. Though that's never a good plan, because if something's really rare, it may never happen again. So, whatever. But at least you know. When I was in first year, I could not remember Newton's method. I couldn't remember whether it was the derivative on the top or the bottom. And I couldn't remember whether it was a plus or a minus. And so I needed a way of figuring it out from scratch just in case I forgot the details. So if that sort of thing helps you, then I'm glad. That's nice. And it certainly helped me. Okay, and here's how to do it. What was it? Let's do the function we had before. All right, find a zero of that other than x is equal to 0. I don't know, let's go 2 decimal places. Let's have more accuracy than the other one. Okay, so we're going to use Newton's method this time. So f of x is sine x minus a half of x. So f dashed x is cos x minus a half. Sweet. And so my formula is going to go that xn minus f of x, which is sine x minus a half of x, over cos x minus a half. xn. Right. That's how I'm going to do it now. And so I just need to pick a starting point. Well, 2 seemed not the worst plan because we already had it. Classic exam question goes, prove that there is a 0 between 1.5 and 2. Now use Newton's method to find it, and so you just pick one of those points. So I'm going to pick x equals 2. It's usually a good idea to pick a point that's not near one of the turning points. So that this turning point, cos x would be equal to half when x was what? Pi on 3. So you don't want to pick pi on 3. So you don't want to pick something near pi on 3, and 2 is not near pi on 3, so that's good. So let's pick x0 to be 2, and then we'll just keep going. So x1 will be 2 minus sine of 2 minus a half times 2 over cos of 2 minus a half. Could someone calculate what that is? Be careful with your brackets. I get 1.99, no, 90099. So we only need 2 decimal places, so I'll do 3 decimal places. 1.901. So my x2 here's where it's really helpful to have a calculator that's smart enough. So it doesn't, not a graphics calculator, but a scientific calculator that's smart enough for you to be able to go back and edit what you've already got in there. In fact, if you've got one that has a memory that you can call x, which a lot of them do, then it's really useful to just be able to type in your calculator x equals and then just go back and repeat it, what you've done before. Or, if you're being very clever, to use the answer button and say answer minus sine answer minus sine 1 of answer, and just keep pressing equals 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 until you get something. One. 1.901. What does everyone else get for that? I get 1.945. So if I just keep doing that over and over, currently I haven't narrowed it down to 2 decimal places yet because my second decimal place keeps moving. Oh, that was x2, sorry. No, that's equals 1.995. x3, by doing the same thing, And here's one I prepared earlier, 1.906. Looks like I'm flip-flopping up and down a little bit, but I should settle down. x4 equals, I'm just going to skip it and just... Oh, wow. I chose a bad starting point.
I think when you were x2 term, the answer you got was taking away the value from 2 rather than taking it from 1.909.
Ah, you're right. Ah, awesome. That just goes to show that you need to check your work. Yes, you're right. When I did it in my calculator here, I didn't change what this number was and I left it as a 2. That would completely explain everything that's going on. Let's just put that one over there. And I get 1.896. And the next 3, if I do my working, comes out to 1.896. Again, rounded off. And so it looks like 2 decimal places, it's 1.90. Yeah. Yay. Beautiful. So, that's Newton's method. That's pretty much all there is to it. There are situations where it will get wildly fluctuating, and then it will settle down. There are situations where it will just get further and further away. If you've got something like sine and you just accidentally get near to one of the turning points every time. There are ones where it will go back and forth between 2 numbers if you pick exactly the wrong numbers. But overall, it should work out okay. And round off will do enough to actually get you closer, strangely, than you would. So you probably, if you were writing this in paper, you should say that you've rounded off to the 3 decimal places each time, so that the person reading it knows that you know that that's not the exact answer. And that's pretty much the deal with Newton's method. Yeah, so now I've talked about the bisection method and its philosophy. I've talked about the Newton's method and its philosophy, and also how to derive the Newton's method formula. How do you feel about that? Can I stop and move on to something else? Excellent.